I should be able to hit animate, no, not animations. What am I doing here? Slideshow from beginning. Okay, can you see the slides? Huda, can you see the slides?
Yeah, I can see
Okay,
that.
great. Excellent.
Thank you.
Okay, let's go ahead and get started. Thank you. Okay. All right, so today we're going to talk about, we're going to sort of start our little 3-week excursion into longitudinal models in SEM. So this week and next week, we're going to talk about growth modeling so we'll do growth curve modeling using structural equation modeling. So this week, we're going to kind of lay out the basics. We're just going to fit a standard linear model, talk about lots of stuff. Then next week, respond to that. Yeah, well, I didn't. You're probably feeling that way too. Like, I don't want to respond to that either. Okay. Yeah. Anyway, I don't know why I sometimes randomly get. Yeah. And then next, oh, there we go. Let me see what our handout is. Here's a handout. I don't know, were there any other extra ones? I was gonna say.
There were in our row.
Okay. And then next week we'll do some nonlinear models. We'll do, what are we doing next week? Piecewise models, I think, and quadratic cubic models, so polynomial models. And then the week after that, we'll talk about autoregressive models in SEM, which is a totally different kind of model, which we'll get into in a sec. So with that said, let's go ahead and jump in. Okay, this is probably already an oversimplification when I say there are sort of two basic models, sort of two basic kinds of longitudinal models. But I should probably say there are at least two. But for sure, we can really think about there being two, again, at least two very different ways of thinking about modeling sort of stability and change across time. So the way that we're going to talk about today is we're going to model growth. But let me just sort of talk for a second about this other idea, which is, maybe I'm interested in how is where I am today sort of influenced by where I was yesterday, right? So like there is some stability across time. I am, right? There's some where I was predicts where I am predicts where I'm going to be. But then there's also this sort of stochastic element that comes in as well. That it's not completely deterministic either, right? And those are autoregressive models. And so we will talk about those in a couple of weeks. But for today, we're going to think about growth models. So sort of the idea here is, okay, I think there is some sort of growth or development across time. So I think that, and this, again, it's going to sound really basic and simplistic, but it's actually a really important point to keep track of. If I'm going to model growth, I have to believe that people are systematically changing across time. Now, again, yeah, duh. But in the first model, in these stochastic models, I don't necessarily have to believe that people are systematically changing over time. That, like, the population as a whole is getting, stronger at something as they get older, or, taller or whatever. I just, I think that I can predict where I am with where I was, and I can predict where I will be based on where I am. But there may not be any kind of systematic increase or decrease in whatever the variable is. And in fact, sort of traditionally, autoregressive models don't even model means at all, which is probably why I've traditionally done them first in this class. But I decided to reverse the order for other reasons. But think about everything we've done in class to this point. we've never thought about mean structure for anything, right? So today is the exciting day in class where we're going to start to incorporate means and intercepts into our models. And these are going to come in really handy when we do growth curve modeling. And they're also going to come in really handy when we do any kind of multiple groups kind of analyses that we're also going to tackle after we finish our longitudinal models. So for this sort of second half of the semester, with the exception of the autoregressive models that we're going to talk about in a couple of weeks, the vast majority of the models that we're going to look at sort of for the next several weeks, we're actually going to be incorporating means and intercepts into our models, which again, like, I mean, probably before you took this class, it would have seemed really weird not to have means, but now you've spent a whole half a semester not thinking about means. So now you have to like get back in the mean business again. All right. So in these growth curve models, right, we think there's going to be some sort of systematic increase or decrease across time, right? And there's going to be some kind of structure, some kind of form to that change. Again, this week it's all going to be linear. We're going to stay with simple linear models, but so there's some sort of everybody, right? There's people are either, growing or, increasing or decreasing. Different people don't have to always be doing the same thing though, right? So it could be that there's change across time and some people could be increasing and some people could be decreasing, right? So we'll talk a bit more about that. But again, we sort of think you could fit a growth model and have on average no growth, but again, it's not particularly interesting. We kind of believe that the population, something's happening, right? There is some expected change in the trajectory across time. Okay, I've belabored that point. So let's move on. Okay, this is my little growth modeling slide. So this is obviously nonlinear change. Interestingly, growth modeling articles have this has kind of become a sort of a hot topic in the 21st century. So you can see that, between, I divided this by decades, and this is just a really quick psych info kind of search. But you can see that there were not that many articles published for all of the 1980s in terms of growth modeling, and even through the 90s, there were very few published articles in growth modeling, and then things have just exploded, right? So, between 2010, 2019, you have, I think it was about over 2,700 growth modeling articles in that 10-year period. So there's growth and growth modeling, very meta. All right. So when we think about, let's just kind of conceptually think about this for a minute. When we think about modeling change across time, so we need to be sort of thinking conceptually about, what are we expecting, right? Are we, again, we want to make sure we're expecting change of some sort. So are we expecting change? Are we expecting to see growth or decline? Either one of those is fine, right? Do we expect that change to be linear or nonlinear? So what is the shape of the growth trajectory that we would expect to see? And these are things, by the way, you should be thinking about before. Obviously, you should think about it before you model your data, but you should really be thinking about these things before you collect your data. Because if you want to model a nonlinear growth trajectory, as we'll talk more about next time, you have to have more observations across time. So as I'll tell you in a minute, to do a basic linear growth model, you must have at least 3 time points. That's the rock bottom minimum. If you want to model quadratic growth, let's just say, the rock bottom minimum number of time points or observations across time is 4. For a cubic model, the rock bottom minimum is 5, which doesn't mean that that's a good number. That just means you have to have at least 5. So if you are expecting more sort of complex growth trajectories, it's important to actually collect more observations. So if you think you're interested in something that you think actually exhibits nonlinear growth over time, collecting only 3 observations across time isn't going to allow you to actually model that complex function. So that's what I'm saying. It's really, really, really important that you think about this up front before you ever collect data, because obviously once you've collected the data, it's too late, right? If you're like, oh, I really should have been, like, I really think this is going to follow this more complicated trajectory, but I only have 3 time points, well, then you're sunk. Then you can't model that. So we want to be thinking about this before we even collect data. Well, I think you just need to know about that conceptually. It's not actually going to change, whether what it's going to mean is you have either a positive or a negative growth slope. It's not really going to change your decision necessarily about how many time points to collect, but I mean, I think you need to be thinking about that conceptually up front. Like, what are you expecting to see, right? Are you expecting people to increase across time, decrease across time? Neither, right? I mean, so you should have in your head before you ever collect data, if you're going to do a growth study, like, what is your theory of change? And in fact, Jack McCardle, who wrote this really nice book on longitudinal structural equation modeling and who died very recently, sadly, would always say when he talked, and he says in his book, this sounds like a really silly, like very simple quote, but I think it's really deep too. What's your model for change? Like basically everything about growth modeling, or not even growth modeling, just longitudinal modeling. What's your model for change? That's the question you always need to be asking yourself. And that's really important. So and again, maybe like, I don't know, it's starting to sink in at this point in the semester that like this whole class is not just about learning these like discrete statistical techniques, but it's also about, I mean, when you're modeling, you got to have a model. And to have a model, you got to have a theory, right? And so much of what we do in this class, and again, I can't, we can't go into depth into your own research in here, right? I'm teaching you all these techniques, but, in some sense, I feel like I do disservice to some of that because I give you these homework assignments where you don't really know. I mean, like, it's a different assignment every week. You don't know the theory. I ask you to use your common sense. But like, for real, if you're going to do modeling, you've got to have theories. You've got to be thinking deeply about your data and your expectations. This is not and I don't mean point and click as in compared to like syntax, but like this is not a point and click procedure where you're just like, I got longitudinal data. Click, tell me what's going on. You've got to be the sentient being here and really think this through. So this is just another example of that. Anyway, so we want to think about that. And then once we actually have data, we're going to be sort of thinking on 2 different levels a bit about these data. Like, how well can I fit people's individual growth trajectories? So I'm going to be really interested in like, how do intra-individual change over time, right? Like, how do people change across time, and how well can I actually fit a trajectory, like to that person's change, right? And then there's a sort of a more macro level question, which is like, okay, well, how similar or different are people from each other in terms of where they start out and how fast they grow? Or, we can set those questions a little bit differently depending on how we center variables. We'll talk about that. But are people's growth trajectories, are they similar to each other or are they different from each other? So how well can I fit growth trajectories, like for each person, right? And then once I've done that, how similar are people in terms of the way that they grow? And of course, the next question is, like, if people are really different from each other in terms of the way that they grow, can I model that? Are there predictors, right? Are there covariates or the things that you're studying maybe that you think might be related to why some people change more quickly and other people change more slowly, right? Or some people start higher and other people start lower, right? So there's this, how different are people from each other? And then assuming people are different from each other, and they always are, anybody who's in the social sciences knows that, right? Then can I explain those between person differences in terms of people's where they start and how fast they change? All right. So how does the outcome, again, basic questions. How does my outcome change over time? And how can I predict differences in those changes across time? So as I said a minute ago, to do growth modeling, we have to have at least three time points. We have to be collecting data across 3 points in time. So when I say 3+ observations, that's not people, that's observations across time. I need to have, this is really important, I need to have some sort of substantively meaningful metric for time, and it should be, what if I call it? It should be equal interval-ish, right? It needs to think, we're going to think of this as our time clock. We need some sort of a clock, and that's going to clock the passage of time in our data. Because again, if you're, this just goes, this just makes sense, right? Anytime you, we could actually go back here for a sec to my really simple graph, right? On the x-axis, I have time, right? And on the y-axis, I have whatever my outcome variable is. So anytime you're looking at, any kind of growth trajectory, you have some sort of time measure on the x-axis, right? And the y-axis is whatever the outcome is. So we need something that captures time, so it's not just enough to know I've got 3 observations across time. I need to know, like, are they spaced out a week apart, a year apart, a decade apart, right? That's going to be really, really important. And I need to be able to have them be, equal, I'll call it equal interval-ish, but basically equal interval, so that I can actually sort of, have a meaningful x-axis, right? So they should be, again, sometimes our measures are more precise than other times, but they really do need to be on some sort of equal interval scale. All right. Again, third, we need an outcome that changes systematically across time. It's not very interesting to fit growth models if your outcome does not change across time. And then we need the dependent variable to be scaled in such a way that we can compare it across time. So it could be that we're measuring the same variable across time, and a lot of times when we do studies with adults, we might be giving them like the same self-report task or survey or whatever across time, and that's fine because it's the same thing across time. When we're doing more developmental stuff with kids, often we can't give them the same test across time. That doesn't, make sense, right? So for example, if you're looking at kids, reading or math abilities from kindergarten through 12th grade, you can't actually give the same test to a kindergartner that you give to a high school student, right? So for those kinds of studies, you need to actually, you don't, probably, unless you decide to become a psychometrician, somebody needs to actually, scale that latent variable, basically come up with a vertical scale for that latent variable so that you actually have a score that is comparable or equatable across time. So for example, with the smarter balanced assessment that the kids take in Connecticut, there is actually a vertical scale score so that the scores do go, it's been scaled from 3rd through 8th grade, and the scores go up across time. But, prior to, I don't know, probably a decade or so ago, a lot of state assessments did not have any kind of vertical scale built in. So they were standardized sort of, or there was information within grade, and so you knew sort of what the average 3rd grade student would score on the 3rd grade test and what the average 4th grade student would score on the 4th grade test. And there was a lot of work done within each grade level, but you couldn't necessarily actually take the 3rd grade score and the 4th grade score and compare them because they weren't on the same scale, and then you also have to be careful because things that might look like they're on the same scale, and this is kind of a goofy example, but aren't necessarily. So my favorite example is let's say you're looking at spelling. And so you collect spelling test data from kids in schools, and they're taking spelling tests every week, right? And they've got their score from, it's the percentage of spelling words that they got correct that week. Well, okay, they're all percentage scores, right? But you can't look at growth because they're different words every week. So like, you know, if a kid gets a 80% every week for the whole year, that doesn't mean that they didn't actually grow in terms of their spelling knowledge, like, because every week they were getting new words, right? So even though their sort of percentage score stayed constant across time, they were learning stuff, right? So again, if you wanted to do some sort of a spelling assessment and look for growth across time, you would want to create something like the entire, let's say, a sample of all the words you're going to teach for the year that you give at pre-test and maybe, you know, at the mid-year and at post-test, so that you have, you know, like 100 words out of the 500 that you're teaching that span across the year. And then you could look to see, like, did kids actually learn to spell more words across the year, right? But you can't just take like the percentage scores for any achievement test that's like a, you know, a teacher-made achievement test, that you're not going to necessarily expect to see growth in those scores. Yeah.
What if you don't expect to see growth, like say as your model and your dependent variable is intelligent activities?
Yeah. Well, if you don't expect to see growth, then growth models are not for you. So there are other, we're going to talk about autoregressive models, which are the one other major category. That is probably, you know, like, you don't want to, if IQ is your thing, if IQ is your jam, I would argue growth modeling is not the way you want to go. You're going to want to tune in for autoregressive models, or, you know, or longitudinal factor models too. But yeah, not growth. Yeah.
On the achievement test, when it just says scale score, is that the vertical scale score?
Well, maybe. I mean, sometimes it is and sometimes it's not. So like for you, it's your job as the researcher to find out, is that a vertical scale score or not? And I'll tell you. So we've been collecting data for a couple of different projects from school districts, and school districts don't even necessarily know what they've got. So, you know, we'll say, like, we want these data, right? And then we'll get the data from the school district, and we'll peek, and we'll be like, this is not what we, you know. So we've gotten all kinds of crazy things from districts. So, and there are all kinds of different scores that are actually often delivered to districts or to schools. So they might, you know, if they get their data file electronically, they may get like 30 different, you know, columns in that data file, all of which have, you know, slightly different names, right? So you be really careful and make sure. So it may or may not be. Scaled doesn't necessarily mean vertically scaled. Usually if it's a developmental scaled score, it'll be a vertically scaled score. Otherwise it could be, but you've just got to double check. Okay. So those are kind of, these are, you know, we've got to have that, right? Okay, so, you know, you need more than 2 waves of data to really measure growth in any meaningful way. Why can't I just do it with 2 waves of data? Well, I mean, they're probably, you know, I would argue 2 of the major reasons are, first, we can't really discern the shape of a person's individual growth trajectory with just 2 waves. Now, to be fair, we can't really do a great job of discerning the shape if it's a nonlinear shape with 3 waves of data either. So, you know, more waves of data are better if you think that the trajectory is going to be nonlinear. But, you know, 2-wave studies really don't get you there at all. You don't know, like, did the change occur immediately after the first assessment? Was the progress steady or delayed? I mean, you don't know any of those things. But even more importantly, I mean, that's important, but you know, that could argue for, you know, more than 3 waves as well, or more than 4, or whatever. But even more importantly, 2-wave studies cannot distinguish between true change and error, right? So, you know, measurement error is like a constant theme in this class, right? That everything is measured with error. So imagine that you have a situation where, like, you measure somebody at pre-test and you measure somebody at post-test. But we know that both of those scores are measured with error, right? So what happens if, you know, at pre-test, let's say the measurement error is, you know, positive, right? The person scores higher than they should have. And at post-test, let's say the measurement error is negative. The person scores lower than their true score, right? So what happens there when you are actually estimating the amount of growth based on that change score, you're going to underestimate the amount of true growth there because, because the person's pre-test score is a little too high and their post-test score is a little too low. Yeah.
Does the same apply when we're using latent constructs and trying to kind of separate out the measurement error?
Well, with latent constructs, we do separate out the measurement error, right? So we are going to use growth. These growth parameters are going to be latent constructs, actually. So that's where we're headed. So I'm just saying, if you just have like two scores and you just create a different score, that's not a latent construct. You're just taking two observed scores. You're subtracting one from another. They both have measurement error. Now the different score has measurement error baked into it. There's no way to figure out how much that measurement error is, right? So that's problematic. But if we have at least three waves of data, then we can actually parse out the measurement error from the true change. And if you think about this, can I draw on here? I don't know. I'll try. Okay, if we think about this. Anywhere that I put 2 points, anywhere in this room, if I put 2 points, right, I can connect them together perfectly with a straight line, right? But if I have 3 points, let's say, I'm gonna draw 3 points there. Okay, now imagine fitting a straight line to these 3 points. It's not going to fit perfectly anymore, right? But I can fit a straight line there. It's not as straight a line as it probably should be, but you get the idea. I fit a straight line there, and now look, this is actually going to be my latent growth trajectory. That line that I'm fitting, which is latent, right? It's not observed in the data, but this is going to be, right? That's really the sort of the predicted slope, but that's like the slope for this person. It's like their latent trajectory. And then, if you think about this, we have how far their actual point is from their model predicted point. This is actually like time-specific error, right? So with again, it has to be a linear model, because if I had 3 time points and I tried to fit a nonlinear model, well, now I can fit it perfectly again, right? So, with three time points, I'm limited to a linear model to actually do this, but with 3 time points, I can actually fit this trajectory, and then I can look at how well, so I get a trajectory, and then for each person, then I can also see, like, how well am I doing fitting each person's trajectory, right? And so there is a residual at each time point for each person. And then you can imagine, because we have a bunch of people, there's variance in those errors across people, right? All right. So we need more than 2 waves of data. And just one other thing, we've got to think, our outcomes do need to be equally valid. Of course, outcomes aren't valid, inferences are valid, but we need outcomes that are not just sort of scaled the same way across time, but they also need to we need to be able to make valid inferences from them across time. So for example, if you give a multiplication test, that might give you a good sense of kids' mathematical skills when they're in grade school, right? But it's really just going to be a simple multiplication test. It's actually not going to be a math test for young adults, right? It's a memory test. So you need to think about that too. And then we won't talk too much about this, but reliability in general, reliability of change measurements depends directly on the reliability of the outcome measure. So, even though we're going to use this way of sort of fitting these latent trajectories, it is always going to be better to have more precise measures if we want to be looking at change across time or growth across time. So the reliability to measure change actually depends on the reliability of the outcome measure, but it also depends on a couple of other things too. It depends on how many times you collect data, so how many observations across the time, and also the spacing of the waves for data collection. So sort of the reliability to estimate individual change is really a function of the reliability of the outcome measure and the number and spacing of the waves of data collection. So, okay. So there's a lot of conversation when you look in the growth curve modeling literature about time structured versus time unstructured data. So if everybody's assessed on the same data collection schedule, which is really going to boil down to meaning that the difference between, like, when the first time points data are collected and when the second time points data are collected, the difference in time between time 1 and time 2 and time 2 and time 3 is the same for everybody. Not necessarily that the difference between time 1 and time 2 is the same as the difference between time 2 and time 3. So I could measure my first measure at the beginning of the study, the second measure could happen 3 months in, and the third measure could happen 6 months after that. So you can see that, that's not, the timing is not necessarily, the spacing is not necessarily equal across time, but everybody follows the same data collection schedule, so that I'm collecting everybody's data, 3 months after time 1 for time 2, and 6 months after time 2 for time 3. So everybody's on the same data collection schedule. That's what's considered time structured data. For standard SEM, and I will talk next week actually about how you can fit time unstructured data in Mplus, and it's actually, there are like 3 different ways. It's not that hard. But sort of the standard SEM approach to latent growth curve modeling assumes that we have time structured data. So for this week, and again, sort of in general, the standard SEM approaches really work well with time structured data, not time unstructured data. So multi-level modeling techniques are really sort of naturally better suited to deal with time unstructured data. And the reason that that's true, sort of in a nutshell, is that when you fit a latent growth curve model, or an individual growth curve model in a multi-level framework, you are actually going to use a long file. So each person is going to have multiple rows, and each observation across time is going to be a row in the file. And then what you end up doing is you have an independent variable for time. So time becomes like an actual independent variable in your data file. And because it's an actual independent variable in your data file, it's really easy for that to take on, it just needs to be, it can be continuous. It can just take on any value. It could be decimal, whatever, that's fine. But as you're going to see in a minute, the standard SEM approach is actually, time is going to be actually, the information about timing is going to be contained in fact.
Could you say
Stop. The information about timing is going to be contained in the factor loadings. And so we're going to have just one set of factor loadings for the entire sample. So, multi-level, if you have completely time unstructured data, standard multi-level models handle time unstructured data much more easily than structural equation models do. So that's like, it's like a pro for MLM for growth curve models. Pro on the side of SEM, and there are a couple. One is it's much easier to model the variance covariance structures in SEM. We have much more flexibility about how we sort of think about the structure of the errors in SEM. And it's also much easier to fit multivariate growth curve models in SEM. And third, it's much easier to incorporate that growth model into a much larger structural model in SEM. So there are definitely some advantages to SEM for growth modeling. But, so this is where if you're really going to do a lot of growth modeling, it actually does pay to know how to do it in both frameworks, because there are times where multi-level is going to be your friend and other times where SEM is going to be your friend, depending on what you need to do. All right. Last point, obviously non-random attrition is never a good thing, but individual growth modeling does not require balanced data. And this is a huge, actually, this is a huge advantage of growth modeling, either in an SEM or a multi-level framework versus sort of using repeated measures ANOVA to do any kind of growth modeling. Because if you sort of do standard repeated measures ANOVA, what's going to end up happening is that anybody who's missing an observation at any time point ends up getting list-wise deleted. And then the only way to deal with that is to do some sort of, multiple imputation. So that's a drag. Okay. But I don't think anybody uses repeated measures ANOVA anymore for growth. So that's probably a good thing. All right. So as I said, with linear growth curve models, we have at least 3 time points for each individual. And you could sort of, again, conceptually imagine that we could, for a linear model, we could fit a straight line for each person through their swarm of points. So imagine like each person separately on their own little, XY axis, right? X is time, Y is is where they are on the outcome variable. And you could imagine, like here, each person's measured at 4 time points, right? And so, okay, you could plot their observations across time. And then you could imagine fitting a straight line to each person's observations separately, right? So if you look at the little individual growth plots that we have here for these 12 people, you can see that, obviously sort of fits better for some people than others. And you can see too that people don't necessarily start at the same place and they don't necessarily grow at the same rates, right? But what I've got here is I can fit a trajectory for each person in my sample. And then, I can see that I could sort of imagine thinking about where do people start and how fast do they grow, again, as being things that I'm really interested in thinking about across people. And then I can look at how much, so on average, where do people start and how fast do they grow? And then how much variability is there across people in terms of where do they start and how fast do they grow? And then finally, how much how well am I able to actually predict people's trajectories with their data points? That's really getting at that sort of intra-individual residual variance. So if you just look at these 12 points, you can see that, some people, there's a lot of variability, right? Some people start really high, like this person, this number 12, right? And some people start really low, like this person, right? And some people grow pretty quickly, like this person starts low but grows quickly. This is really sad. Assuming that's something we want to grow. This person starts high, but then is actually declining across time, right? So we've got negative growth here, positive growth here. And then this person is actually starting pretty high and not growing at all. So we can accommodate all of those different patterns with growth curve modeling. Because again, we're thinking about, sort of these, conceptually, we have these individual growth models, like we have these individual growth curves. Each person has their own latent trajectory, and then we can ask how much variability is there in terms of where people start and how fast they grow. Those become really interesting questions, and then we can also ask about how much error is there around those trajectories. All right.
Betsy, this is something
Yeah.
that you would look at in this way. I know this is like an example of 12, but is this something that you would look at the individual level?
Is it something I look at the what level?
Individual level?
Yeah, I do always like to start, before I do any kind of growth modeling, I always start by just, looking at sort of average trajectory, which is super easy, but then also looking at these individual growth
Even
plots.
if there's like 500.
Yeah, exactly. You could do like the first few hundred people or random sample of people. You got to be really careful. Well, it's not a problem here when you're in a wide format, but if you're doing it in a multi-level format, you have to be really careful about randomly sampling because you want the whole person, not just randomly sampling time. That can be bad. But yeah, you can just get a random sample of people or the first 500 people or whatever and get a sense of what those individual growth plots look like, and there are easy ways to do that. Yeah.
Would you ever draw like a longitudinal outlier? Is that a thing where this is not a great case because it does look like there are several where it's maybe a little bit of a downward trend, but it's like if everybody grows and one person is declining, would that be explained by something outside of?
I mean, if everybody's growing and one person's declining, it could be explained by something that's going on with that person, right? I mean, so can it be that everybody looks like they're kind of doing the same thing and there are just, one or two people who look really different in terms of the way that their growth is going? Yeah, sure. I mean, that can happen. Like when you say outlier, I feel like there's a little bit of a judgment there. I think that's fine. People are different. I wouldn't necessarily remove them or anything, but yeah, I mean, I think that's not actually that uncommon. Again, I do a lot of stuff with achievement, in kids, especially in elementary school, and the vast majority of kids do grow in terms of their reading and math achievement. Some grow more quickly and some grow more slowly, but it's really rare for achievement data for a kid to actually go down across time, but it does happen. It's sad, but it does happen. And there may be a very logical explanation for why it happened, right? And you may have access to that, or you may not have access to that. But yeah, I mean, the nice thing is that, there's a lot of flexibility if you think about it. Every person, we're fitting a straight line trajectory to every person here. Again, conceptually, right? We're not going to actually do any of this sort of empirically. I mean, we're not doing this. But conceptually, we're fitting a straight line trajectory to every person, but every person can have a different slope and every person can have a different intercept. So even though, straight line seems very limiting, and it is in ways that we'll talk about next week, still there's a lot of flexibility to model different kinds of trajectories for different people because people can start at different places, they get different intercepts, and they can grow at different rates, including being positive, negative, or no change at all. All right, so latent growth curve models are going to incorporate information about the population, and again, if you think about if you're doing research on change and growth across time, one of the things you're definitely going to want to report is like, okay, well, on average, what's expected? What's the expected place where people start? What's the expected rate of change? So on average, where do people say we're going to be looking at reading, in our example, we have PIAT scores, and it's reading scores at ages 6, 8, and 10. So it's every other year. And the kids are approximately, approximately 6, approximately 8, approximately 10 years old. So, okay, so it's reading. I'm certainly going to expect them to increase in reading, right? But I could be interested in okay, on average, where do kids start? What are their reading skills at age 6 on average across my sample, right? Or what's the expected value, sort of, for a kid's reading at age 6, and then how fast do they grow in reading, between ages 6 and 10, right? Or between ages 6 and 8 and 8 and 10. So the expected value for the intercept, that is actually going to be the mean of our intercept factor. And the expected value for the slope is going to be the mean for our slope factor, which I'm going to show you in a second what our model looks like. So that's really telling us about sort of on average across everybody, where do we think people are going to start? How fast do we think people are going to grow? But then we're also going to get information about the variance of the intercept and the variance of the slope. And the variance is telling me about how much between person variability is there in terms of, both, where people start and how fast they grow. So if everybody seems to be growing at the same rate, so everybody grows at essentially, everybody makes about the same amount of progress across time, then I would expect that the variance in the slope would be very low. So if you got a slope variance of 0, that would be saying everybody's growing at exactly the same rate across time. And I thought I had a picture of that somewhere. Hold on, let me see. Okay, well, if I do, it's way back. It's way, no, I have to, here, let's go this way. Where was I? Okay, I can draw a picture of it though. So,
Betsy, question.
Yeah.
Are linear and latent growth like the same terms that we use interchangeably?
well, linear really means I'm fitting a straight line trajectory. Latent means the trajectory is like, it's not observed, right? I'm observing the observations, but then I'm fitting a trajectory to it. So latent growth curve models, we're really talking about, fitting a latent trajectory to the observations across time. That latent trajectory could be linear. To this week, it's gonna be linear.
Okay.
Next week, we could have latent trajectories that are not linear. So they're not actually the same thing. But this week, everything is a latent growth curve model that is linear. All right. So now, imagine that people start at different places, but if my slope variance is 0, that means everybody grows at the same rate. So what does that look like? If I put them all on one graph, it would look like that, right? That would say, if you think about that, that says like, oh, different kids are starting in different places, but they're all growing at the same rate. By the way, bad news there in the sense that if all kids start in different places and grow at the same rate, they're never going to end up in the same place, right? Because, I don't know, but I digress. I won't editorialize. So now imagine something else though. Imagine that everybody starts at the same place and they grow at different rates. That might look like this, right? So I've got, everybody starts at the same place here, but some people grow really quickly and other people grow really slowly. And by the way, depending on where you sort of center your variable or where you sort of start data collection, this might not be that uncommon, although you're sort of throwing away some good parameters, which we'll talk about later. But for example, like, let's say I'm looking at little babies' language development, and I start at birth, right? And I start measuring kids every, 3 months from age 0 to age 2 or 3 or 4, whatever. Well, first off, that's not going to be linear, but play along for a minute. Point is that if you go to a whole bunch of neonatal units and you test kids' language, as soon as they are born, I don't care how brilliant the kid is, you're going to get a 0 for everybody, right? No kids are speaking in the first few weeks, right? I mean, I used to work at the National Center for Research, well, I still do, but I used to be a GA over there, and sometimes we get these crackpots who would call up and they'd be like, my 6-week-old is speaking in sentences. And I'm like, I really don't think so. But even so, we never got anybody who said the kid was born yesterday and their speech is done. Guaranteed, if you center at birth, you could get variability on height, right? Number of inches. You could get variability on weight. You could get variability on APGAR scores. You could get variability on lots of things with babies. But you're not going to get variability on like fine motor skills, reading skills, speaking skills, any of those things, right? So then everybody would be starting at the same place, but now they're growing at different rates. And that's what that would look like. So that would say, oh, there's no variance in the intercept where people start, but there's lots of variability in terms of how fast people grow. I mean, usually we're going to have variance on both of those things. So the variance here is going to tell us about between person differences in the parameters that we're interested in, right? And these expected values are like, like on average across the population, the stuff that we're kind of used to thinking about, talking about in papers, right? This is like on average, what do we see, right? On average, this is what people look like. Here's how much variability there is between people. And then once we find out there's a lot of variability between people, we can try to explain some of that variability. And that within-person variance, in terms of the errors, that's going to be captured from our error variances. Yeah.
So that means slope is positive.
The
That
means.
means slope is positive for the.
Oh yeah. Yeah. In both of these drawings, the mean slope is positive. Yeah. All right. So I feel like I just said all of this, right? So you can sort of imagine you could draw, and this a lot of times you'll see this actually in papers where maybe there'll be some, it gets tricky though, because if you put too many individual trajectories on a graph, sometimes it gets like unreadable, right? But you'll see like, people put sort of individual trajectories and then they'll sort of put the mean trajectory. So the mean trajectory is really, that's really what we're getting at with those means, the means of our variables. And the individual trajectories, that's really kind of showing us how much variability there is around those expected values. All right, so I feel like I said all of this already. I'm going to keep going. And I did talk about this actually earlier, but just to kind of recap with a much prettier picture than what I was drawing. Once we have a trajectory for each person, the time-specific residual captures the error, which is really the difference between the person's predicted score at that time point, which is going to be on that trajectory, right, and their actual score. So, for example, right, you can see like this is the, for this person, we're actually going to, you would sort of, their prediction would be they're growing, I don't know what the rate is here, but they're growing at this rate. Right? But we can see that like, there is error, like that's the sort of the latent trajectory, but there is error, right? So actually here, we're pretty close, there's not much error for the first time point. But there's more error here for the second, third, and fourth time points, and we're sort of underestimating where they were at times 2 and 4. We're kind of overestimating where they were at time 3. But again, we believe there's measurement error in each of these observations, and that's why we favor the latent trajectory. So again, the idea is the latent trajectory is, we're sort of dealing with the error, right? The latent trajectory sort of, it does not have error. It is their unobserved latent trajectory. And these observations across time, they do have error, but we're able to sort of parse that out again, right? So same kind of thing that we were doing earlier with our CFA models. And you can see that, different people, different people hang tighter to their trajectories. So there could actually, we're not going to do that, but you could actually imagine that there's a different amount of like within-person error across people, which you can model that. We're not going to do that today. But also, there might be different amounts of error variance across time, right? So for example, like with this person, you can see there's very little error variance at the first time point, or not error variance, this is a residual, but the residual is very low at the first time point, and it's much higher at the subsequent time points. You could actually imagine a situation where like as time goes on, there's actually more dispersion, so the residuals get larger around the trajectory. And this is, again, think about when you did regression, you talked about heteroskedasticity, right? So in regression, you talked about the idea that, I'm just going to draw over this, right? Maybe you have this regression line, and maybe, right, maybe the variance of the, maybe there's more variance here at the upper end of the regression, right? And less variance down here, and you probably talked about that as heteroskedasticity, right? Well, you could have the same kind of thing here. You could have, but now it's going to be like in the individual trajectories. Like it could be the case that, there's more measurement error. You're doing a worse job sort of predicting people's scores as you go across time, which would be, the same idea of like heteroskedasticity, right? So we can model that really easily. Yes?
So would this be like a violation of stationarity, like if we were the time series data?
Yeah, I mean, so let's put that question in the parking lot, because we're not treating this like time series data. That's really, I think, we'll come back to it when we get back to the autoregressive models, which really are much more like time series data. What it is it's, I mean, again, I think of it as like heteroskedasticity. It really is that the error variance is getting larger across time. I don't think it really is necessarily a violation of stationarity, though. All right, but again, that's kind of a whole different ball of wax. All right. So our key parameters in our model are the slope, the rate of change, and we're going to model a mean and a variance for the slope, right? And we're going to have an intercept. Now, just like anything in regression, how we interpret the intercept is going to depend on how we sort of code our variables or center our variables. But the most common way that people will center time in growth curve models, and it's not the only way, but the most common way is that people will center time at the initial starting value or at an age that is basically at the beginning of the study. And I'll show you a bunch of different ways that we can sort of code or center time. But if we assume that we're going to sort of center time at the beginning of the study or center time, sort of at the start, then the intercept is going to be able to be interpreted as where do people start. And again, in developmental studies, that's often what we're really interested in. We're interested in like where do people start and how fast they grow. We could center things differently. We could have like where do people grow? I mean, how fast do they grow and where do they end up? Or we could center at the middle of the data collection and be like, okay, where are people at age 13? Because that's a really important point in time for my study. And then how fast do they grow? So you don't have to be centering at the initial time point. And again, the last key parameter is really going to be about error. So how far are these time-specific scores from our predicted scores? All right, so there we go. So that's kind of like the general gist conceptually of what we're doing. Well, but to do this, we need to know how to model means in SEM, right? Because I just said we're really interested in the mean of the slope and we're interested in the mean of the intercept. So we need to be able to incorporate latent means and intercepts into our SEM models. And this is going to become really useful for us for multiple groups, for measurement and variance purposes, for multiple groups models. We can actually, when we do this, we can reframe regression, t-test, ANOVA, basically almost any test of mean differences. We could then reframe within an SEM framework if we were so inclined. And then again, we really need it for our growth models. Okay. All right. So remember in the beginning of the semester, we talked about sort of equations, and I said like, let's just ignore the intercept. Right? It looks like in a regression equation, but let's just ignore the intercept for now. Well, now we're bringing the intercept back in. So let's think about just a simple CFA model for a second, and imagine that we've got, your score on Y1 here, right, is a function of, we've been talking about, right, the factor loading times the latent variable plus the error. That's all old. But now I've got this, right? Now I've got this intercept. So what is that intercept? Well, think back to multiple regression. Think back to your regression days. And what is that? What is that? How would you interpret an intercept in a regression model?
The value of y when x is 0.
The value of y when x is 0. Exactly. Perfect. That's what an intercept is always going to be. It's going to be the value on the outcome when the independent variable or all of the independent variables in the equation, if there are multiple, right, are equal to 0. So in this case, our x is actually our latent variable, right? So our intercept here would actually be the mean on y when the latent variable is 0. When eta, the latent variable, is 0, right? Does that make sense? Okay. And I could do the same thing here. I can get an intercept for each of these. So I've got the intercept for item 1 is the mean on item 1 when the latent variable is 0. When is the latent variable 0, by the way? What's the mean of the latent variable? Well, actually, that's not a fair question because we didn't talk about means, right? But okay. Well, here's the thing. How many pieces of information do I have about means? If I have 4 observed variables, how many, like, again, imagine my variance covariance matrix is a 4 by 4. I've got 4 variances, right? And I've got however many covariances. What is it, like 6 covariances? I've got 4 variances. How many mean pieces of information do I have? Yeah?
So it's the same as known, so it's like 20 or?
Well, just the mean pieces of, I'm sorry. I said something wrong. What I meant was how many means do I have? I said mean pieces of information. I mean, how many pieces of information about means? Yeah, 4.
Okay.
Yeah, sorry. The way I said that was super confusing. But I have 4 variables, so I have 4 pieces of information about the means, right? So I have 4 means that are like in my sample, 4 means that could be modeled, right? And you're right. So then if I want to think about the total number of pieces of information I have 4 variances plus 4 means plus 6 covariances. So I think I've got 4, if I've counted right, and I'm doing it on the fly, so tell me if I did anything wrong, but I think I've got 14 pieces of known information there. Before, when we counted, we would have been like, right? We would have said there are 4 and 4 times 4. Well, this is not fair. I'm doing something tricky here. Let me say this. Okay, so there are actually 3 different formulas we can use for counting these numbers, okay? So the one that we keep using is b times b plus 1 divided by 2. And this gives me the number of unique elements of the variance covariance matrix, right? So I can go 4 times 5 divided by 2 is 10, right? But what I was thinking about in my head, but not sharing with you, because I kept saying there are 4 variances, is there's another formula that I can use if I just want to know how many covariances there are. Anybody have an idea what that formula is? I think we talked about it once before.
V times V minus 1.
V, that's right, V times V minus 1 over 2. And this tells me about just the unique covariances. So this is really the off-diagonal elements, right? This one is the diag plus the off-diagonal, okay? So if I go V times V minus 1 over 2, I get 4 times 3 divided by 2, which is 6. Which, okay, that makes total sense because I got 6 covariances, right? Plus 4 variances. 6 plus 4 is equal to 10. And now the reality is, and I guess the reason that I kind of like this a little bit is because however many variances I have, that's going to also be how many means I have, right? So I've got 10, so I've got 6 covariances, I've got 4 variances, and now it's going to be 10 plus 4 is equal to 14 means plus covariances plus variances. So like that's the whole shebang. And there is a formula for that, by the way, which is V times V plus, anybody want to take a guess? 3 divided by 2, which actually kind of makes sense if you think about it, because V times V minus 1, you go up by 2, you get V times V plus 1, right? You go up by, and really, the reason we're going up by 2 is because we're dividing by 2. We're really just adding V. Like, we're just adding V to this to get here, you know? So you could express it like this and just say V times V minus 1 divided by 2 plus V gives you this. But it's quicker to say it this way. And then I could take this, V times V plus 1 divided by 2 plus V. That actually gives you V times V plus 3 divided by 2. And it seems weird at first, but again, it's because everything's getting divided by 2. So that's why we're going up by 2 in the numerator. Okay, point is, however many variances I'm estimating, that's how many not variances I'm estimating, sorry. However many variances I have in my variance covariance matrix, however many variances I have, that's how many potential, in a single group study, that's how many potential mean pieces of information I have. So here, I have 4 pieces of mean information. Now, this is where identification gets like a little bit tricky, because when the degrees of freedom are counted in Mplus, it's going to give you, this is very much like, when we were sort of talking about measurement model versus structural model, and sort of, you just get this overall DF, right? But it's not breaking out where it's coming from. The same thing is going to be true, the same thing is going to be true here in terms of the number of parameters that I'm estimating for means, right? And how many I can estimate for means and intercepts. When you look sort of at the Mplus output, it's not necessarily going to say like, oh, you have 4 pieces of mean information. Therefore, you can estimate 4 pieces, you can estimate 4 parameters that are parameters about the means. It's just, it's just counting the total number of like knowns and unknowns. But the reality is that you can't estimate more means and intercepts than you have mean pieces of information. So even if you have positive degrees of freedom on the variance covariance side, you can't necessarily borrow those positive degrees of freedom to be identified on the mean side. So for example, here, let's just think about our example here with 4 observed variables, right? So we just said we have 14 pieces of information total, right? 10 are variances and covariances, plus 4 are means. How many parameters are we estimating in that simple single latent variable model? We've got 4 error variances, right? We've got 3 factor loadings and latent variable variance. So we've got 8, right? So if you just think about that from what we've done before, we've got 10 knowns, we've got 8 unknowns. So we have 2 degrees of freedom in the variance covariance part of the model, okay? So this is actually over-identified. No problem. We can estimate this. It's a 2DF model. But now, if I want to think about means and intercepts, again, I've got 4 pieces of mean information. I can at most estimate 4 means and intercepts in my model. I can only have 4 mean and intercept parameters in the whole model. I can't be like, hey, I got 2DF. So I'm going to borrow those 2DF, and I'm going to estimate 6 means and intercepts, or I don't know how you do 6, but you might want 5. You could imagine. You might be like, hey, I want to estimate an intercept for each of these variables, and I want to estimate a mean for the latent variable. But you can't do that because you only have 4 pieces of information. So you can estimate these 4 intercepts. But if you estimate all 4 intercepts, then you have to constrain the latent mean. And in that case, you're actually just identified in the mean structure. And that's why way back when you asked about something, I was like, oh, yeah, the parameters look different, but the degrees of freedom are the same. And that's because, generally speaking, what Mplus will do, unless you're doing something else, but it will, like for example, in a CFA model, by default, it will estimate all of the intercepts for all of the, for all of these outcome variables, and it will constrain the mean for the factor to 0, which you may or may not have noticed, but that's generally what happens. So, and that'll generally, again, so the mean of the factor is constrained to 0, and remember, the factor doesn't have any real metric of its own. So remember how we had to scale the latent variable? We had to think about scaling the latent variable before, and we were like, oh, we could estimate a factor variance, but then if we estimate the factor variance, we said we got to constrain one of those loadings to be 1. So it's kind of like the same kind of, it's kind of the same calculation if you think about it in some sense, right? Or we could fix the factor variance at 1, and if we fix the factor variance at 1, then we can estimate all the factor loadings. We actually have the same choice when we get into mean structure. We can either estimate all of the intercepts, but if we do that, we have to constrain the factor variance to be 0. Okay, so we constrain the factor variance to be 0, estimate all the intercepts. The other option is use like what's called a marker intercept strategy. In a marker intercept strategy, we constrain the intercept of whatever was the marker variable. You don't want to like mix and match with 2 different variables. So whatever was the marker variable before, if you constrain that loading to be 1, you can constrain the intercept of that variable to be 0. And then in that case, you can actually estimate the mean of the latent variable. Just like in the marker variable strategy, when we do that, the variance of the latent variable is in the metric of the marker variable. In this case, if you use a marker intercept strategy, the mean of the latent variable is going to be in the metric of the marker variable. So those are our choices. We can either use a marker intercept, so we constrain the intercept to be 0 here for our marker variable, and estimate the latent mean and all of the other intercepts. And in that case, we've used up all of our degrees of freedom for our means and intercepts, because we're estimating 4 things, and we only have 4 pieces of information. Or, and I would say what's more common, is to constrain the latent mean to be 0 and to estimate the intercepts for all of the y variables, for all of the outcome variables. Does that make sense? I know it seems kind of confusing, I think, the first time people hear this, but are you with me? Kind of, sort of? Yeah? Okay. And then let's just say, for now, let's say I do make the mean of the latent variable 0. Then how would I interpret the intercept? We said that the intercept is the expected value of y1 when the latent variable is 0, right? And the latent variable is just going to be 0 then, like that's just going to be on average, right? If you think about it. So if I use that strategy and I scale the latent variable to have a mean of 0, then what I'm going to get back for these intercepts, again, are just going to be the means on the items, because they're going to be the average on the item across the sample. Because the latent mean is 0, and that is going to be like like on average across, right? It's just going to be on average across what I've got. So, so if you've ever looked at the unstandardized, and again, want to look at the unstandardized intercepts. If you ever looked at the unstandardized intercepts for any of the runs that we've done for like a CFA, what you would notice is that those intercepts, well, maybe you probably wouldn't notice because you don't know the data, but if it were your data and you were looking at it, you would notice that those intercepts just end up being the means, again, the means on those items. Like in a simple single group case with a latent mean of 0. Does that make sense? So the vast majority of the time that we're doing latent variable modeling, we don't really have to think. If we don't care about mean structure, We don't have to think about it much. We just estimate intercepts for all of our observed endogenous variables. Our latent variables are generally scaled to have a mean of 0, right? And we need to do that so that our mean structure is identified, and we can just kind of like go along our merry way and not worry about it too much. But we do have to think about it a lot more carefully when we go into the multiple groups framework and when we go into growth curve modeling. And especially in growth curve modeling, given what I just said, which was I want a mean, well, I haven't shown you my model yet. Hold on, let me show you the model. Let me skip that for a second. I got a picture here somewhere. Where's my picture? Okay, there's a picture. Okay. So the way I'm gonna actually fit this latent variable model is, remember I said the intercept is, I'm gonna have a latent intercept and I'm gonna have a latent slope. So, and oh, by the way, I apologize. This is where the term intercept is gonna get like super confusing, because this is the latent intercept, but we could also have intercepts for each of these variables, right? So kind of an unfortunate thing that this is often called the intercept and the, I mean, it is, that's what it's called, the intercept and the slope. So I will try to be really careful when I'm talking, but just be aware, we got two different kinds of intercepts going on here. So, oh, I should also mention that again, this is true for regression too. So if we have an exogenous variable, anytime we have an exogenous variable, we estimate a mean for the exogenous variable, right? Or just like with an exogenous variable, we have a variance, right? So like it's exogenous, it's outside the system. We're not using anything to predict it. So like that exogenous variable has a mean and it has a variance. Any exogenous variable doesn't have like an intercept, right? In a regression equation, the intercept is always the predicted mean when all of the independent variables are 0. So intercepts are always for endogenous variables. So again, this is very analogous to what we've talked about earlier in the semester. We've said if I've got an exogenous variable, I'm estimating a variance. If I've got an endogenous variable, I'm estimating a residual variance, right? And we call that residual variance a measurement error. Right? If it's in the measurement part of the model, we call it a disturbance. If it's a structural part of the model. But if the variable is endogenous, I'm measuring, I'm not measuring. The parameter that I'm estimating really has to do with the unexplained variance, not the total variance, right? Okay, so analogously here, if a variable is exogenous, I'm going to estimate a mean. And so in this case, I'm going to estimate a latent mean for the intercept, and I'm going to estimate a latent mean for the slope. Those are two exogenous variables. Those are two pieces of mean information, not variance information, but mean information. Okay? With me? So, what that means, no pun intended, is that I cannot estimate intercepts for these three variables. Because if I estimated an intercept here, an intercept here, and an intercept here, and a mean for this, and a mean for this, that would be 5 parameters in that mean structure. But I only have as many knowns or pieces of information in the mean structure as I have, observed variables. So I only have 3 pieces of information in the mean part of the model, right? So my mean vector has 3 pieces of information. I cannot estimate more than 3 mean intercept things. Very technical term there. So if I want one here, which I do, and I want one here, which I do, then at most I could actually estimate one, I could estimate one intercept down here. But that's not what I'm going to do. I mean, again, you could. There are lots of things you could do. It would be a little bit That's not how we fix, that's not how we fit a growth model. What we do actually is we constrain all of those intercepts for all of those measured variables to be 0. So what I'm really saying here is I'm gonna say that this intercept is 0, this intercept is 0, this intercept is 0, okay? And I'm gonna estimate a latent mean for this factor, for this intercept factor, and I'm gonna estimate a latent mean for this slope factor. So how many degrees of freedom do I have in the mean structure part of the model? That's right, 1. So growth models are super interesting models because generally speaking, usually for most of our models that we run, we have no degrees of freedom in the mean structure part of the model. So like what's going on with the means and intercepts does not contribute to model misfit at all. But with growth models, that's absolutely not true. We are over-identified in the mean structure part of the model. And so how well we can actually sort of fit, how well these latent variables are able to reproduce the PIAT scores over time, that is really going to contribute to the misfit of the model. So if you think about it, again, like what is the, well here, what is our, like a person's score, let's say, at the first time point is a function of the intercept mean, actually. So this is going to be the mean on this latent intercept. I should do this here. I can probably make this less confusing. Plus, yeah, let me go back. Let me not do it on this slide. Let's go back here. Okay, well, this is maybe a little bit better. Okay, so a person's score, right, at time t, so a person I score at time t, let's say, is a function of that person's intercept, right, plus that person's slope times whatever this time variable is going to be, plus the error. So if you think about what we're, and so it's just a regression model. So if you think about what we're saying, I could use a little drawing here. Let's say this is y1. And I have like, I'm just going to call this initial value, like initial value and slope. Y1, Y2, Y3, E1, E2, E3. Okay, this is my simplest growth model. Looks like there's a lot going on here, but actually I'm going to constrain a whole bunch. I'm actually going to constrain all of these loadings. So I'm going to constrain the loadings here to be 1. So what that's, if you think about what's happening here then is I'm going to get some sort of a factor mean for where people start out, okay? And then it's going to travel through to give me a predicted value on y1, right? Y1 is going to be a function of, so think about here, I really shouldn't be doing this with individual people. I should probably just be doing it overall for the expected value. So let's leave the eyes out of it for a second to make this simpler, okay? So the expected value at time 1 is going to be a function of the factor mean that I'm going to estimate up here. That's that latent variable times 1. Y1? Well, because I constrained the loading to be 1. Plus, here's going to be the mean for the slope. Okay, so this is like the intercept factor mean, and this is the slope factor mean. So the mean for the slope times time. We haven't really talked about how to code time yet. But let's say I want the intercept to be a person's predicted value at the beginning, at the outset, right? So then I can code the slope so that it's 0 at the beginning of the study, right? And then if I do that, then think about, I get the mean slope times 0 here. Mean slope times 0 is 0, right? And so now I get a person's predicted score, or no, not the person's predicted, let's just say like the expected score at time 1, because I got rid of my eyes. But like the predicted score at time 1 is just a function of whatever is the mean on my intercept factor times 1. So what that means then is that the factor mean for the intercept tells me about the expected value for where people start out. So the mean of the intercept factor says, where do people start? And again, because I constrained these intercepts to be 0, right, they're not going to enter into these predicted values at all. So what I'm saying is, I can predict people's scores across these 3 time points with just 2 pieces of mean information. That's really what I'm saying here. I can predict the score. Like I can predict where people are at time 1, time 2, and time 3. So I can get those expected, Y1, Y2, and Y3, and I can do that with just 2 pieces of mean information. So I could be wrong, right? I mean, that's kind of the point. That's sort of where some of the error comes from, right? Is that like I could be wrong because maybe that trajectory doesn't perfectly predict their scores at all 3 time points, but those E's, right? Each person's error is giving me about the information about how far their actual score was from their predicted score. Yeah.
So how come in the slide where you have like the same thing essentially drawn out, how come that slope for time 1 is like a factor loading? Because it should be 0 if it's time 1. Because how do you have this?
Oh yeah. Okay. So in a bunch of the slides, I put like B1, B2, B3, I think, or B0, B1, B2.
Yeah, B1, B2.
B1, B2, B3. Okay. So I did this to be really general because it doesn't have to be 0, 1, 2. We're going to plug in numbers there, but like if I want to center time so that it starts at the beginning and goes up by 1 for each one, then it's going to be 0, 1, 2. But if I wanted to set time so that it's actually 0 at the end, so I wanted to see so I wanted my intercept to be where people end up, then I could go -2, -1, 0. And in fact, you can actually, this is kind of weird, and we'll talk, I think, a little bit more about this next time. I think I make you do this on your homework, though. You can actually, if you have, I think, at least 4 time points, I think you need, but you can set things up so that you just constrain the loadings of the first and last time point. So you could do something like this. You could go like, hold on. That's not working. You could go like 0, I'll put star, star, let's say we got 4 time points. And then you could put 1. And so you could, this model would actually be identified, so you could have like 0, freely estimated loading, and 1. Which, okay, that might seem weird at first, but like, what's that giving you? If you think about the slope is always like the change in y per unit change in time, right? And so if I code this so that I have a 0 at the beginning and 1 at the end, then the total amount of change across the entire data, like whatever, number of observations, that is going to be the slope. And then, and this is where it seems kind of funky, but like then I actually estimate these factor loadings. And if it were going to fit a linear model, like what should these factor loadings be? Like if really you collected things at sort of equidistant measures across time, let's say. Yeah, it should be like, well, it goes 0, something, something, 1.
0.3, 0.6.
Yeah, it should be like 0.33, 0.67, right? Or 0.3333, 0.66666, and 1, right? So, but you could estimate these, and that can actually be really interesting in diagnostic because the degree to which it's not giving you sort of something that feels like it fits the pattern that it should tells you something. So, like, if you do this, and you get, and I've done this before, you can get something like this. You can get 0, star, star, 1. And so, okay, this is going to be 0 and 1. And let's say that you get 0.5, 1.2, let's say, and 1. Like, what does that mean, actually? Well, if you got 1.2 and 1, you actually kind of like overshot, like if you think about it, like your trajectory, you like overshot sort of that whole thing and kind of came back down again, which is really weird, but that could happen. Or you could get something like this, and you could get like 0, 0.1, 0.9, and 1. And that would sort of be telling you, wow, like most of the action is actually between time points 2 and 3, right? And very little of the action is between time 1 and 2 and time 3 and 4. So basically you're letting time be, you're letting those factor loadings that represent time be like really flexible and be empirically derived, which on one hand is very difficult to interpret. I mean, on the other hand, I think can be really useful in diagnostic. So I think they're really cool models. These are called latent basis models. And I think I asked you to do this for homework, actually, is to fit a latent basis model after you fit the original model. I don't necessarily recommend them as like your stopping point for growth models, but I think they can be an interesting, they can be an interesting model to fit, especially when things aren't working well. Yeah.
So what is the difference between that and like a non-linear? Because that seems to me like it suggests that the growth is non-linear.
Yeah. Well, it is one way of sort of dealing with nonlinearity, right? But you're doing it by basically freely estimating the loadings, which, is not actually necessarily completely, is not necessarily exactly the same thing as fitting a nonlinear model, right? But it is a way of dealing with nonlinearity. It's completely atheoretical, right? And again, it's not necessarily like a statistically equivalent model to any of the sort of normal nonlinear models you would fit. And there really isn't anything analogous to this that I know of in a multi-level framework, because again, in a multi-level framework, you have an independent variable for time, right? So you're plugging time in as a variable. Here, time is we're sort of capturing the time. So basically it's like, well, I'm gonna let time be flexible. And then the way that time is flexible does tell me something about the way my model's working. So yeah, it's kind of funky, but it can be interesting, yeah.
In the first example where you made the mean slope 0,
Uh-huh.
we're just doing that for time 2, time 3, time 4. So like the logic of that second.
Oh, so yeah, I should finish that because like here, no, that's okay. Because here, the mean slope was 0. Go back here. It's too messy to look at for a second. But remember that the slope coefficients I talked about were like 0, 1, 2, right? 0, 1, 2, 3, let's say, for the linear model. We got into like, why is it B? And it's B because it could be anything. But most of the time, I'm going to use something like this 0, 1, 2, 3. So here, the sort of like the predicted Y1 is just whatever the mean of the intercept is. But here, at the second time point, the predicted Y2, right? The predicted Y2 is going to be the intercept factor mean. So this is the intercept mean times 1. It's always times 1, right? Because again, if you look at the model, plus we're going to have the slope factor mean. And here it's going to be times 1 because that's the factor loading at time 2, right? And so the predicted Y2 is just going to be the mean of the intercept factor plus the mean of the slope factor, right? And then of course this is the error, the individual error. And then at time 3, what's it going to be? It's going to be, right, the predicted value at, time 3 is going to be always just going to be the intercept mean. That always gets multiplied by 1. That factor loading is always 1, right? So the intercept is always, it's just always going in there as like, what's the predicted score when time is 0? And then the slope is like, how is that changing across time? So here it's going to be intercept mean times 1 plus the mean slope times 2, right? Because I have this code of 0, 1, 2, 3. And then finally, the predicted score times 4 is going to be the intercept mean plus the mean slope times, in this case, 3, right? So I'm taking 2 pieces of mean information and I'm using it to reproduce these means across 4 time points. So in this case, I actually have 2 degrees of freedom in the mean structure part of the model. Because I'm using only 2 degrees of freedom, I'm only using 2 pieces of mean, I'm only estimating 2 mean parameters, and I'm using that to reproduce the information across all 4 of the time points. So I'm over-identified in the mean structure part of the model. I always think, this is going to age me, you probably don't even know this show, but I'm old, so I'll admit it. There used to be a show called, Name That Tune, and they'd be like, I don't even remember who the host was, but they're like, hey, I can name that tune in 5 notes, No, and then somebody else, I can name that tune in 4 notes, right? So I always think of this as like, name that tune. It's like, I can reproduce those scores across time with just 2 means. And that's what I'm saying with the linear model, right? Now, that turns out not to be true. I could theoretically, fit like a quadratic model here. If I do that, then I'm going to actually have, another piece. I'm actually adding another mean to the model. So then I'd be saying, hey, I can reproduce those means across time with 3 pieces of mean information. So this whole growth model, so much of where the misfit is in a growth model is really about the mean structure of the data. It's about whether I can reproduce the means across time with the latent mean parameters that I'm estimating in my model. Does that make sense? So in this model, by the way, how many degrees of freedom would I have on the variance covariance side? Let's count that out. We've got 4 time points, right? So what are we estimating? With 4 time points, we're estimating 4 different error variances, right? We're estimating 2 latent variable variances. One is the intercept, right? The intercept latent variable, and one is the slope latent variable, because they're both going to have variances. And then we don't have the picture up here, but if you look in your handouts, we're always drawing a covariance between the intercept factor and the slope factor. So we're going to estimate one covariance between the intercept and the slope factors, right? And actually, we're not estimating, and again, with these standard models, we're not estimating any factor loadings because they're all constrained. All the intercept ones are constrained to 1, and all the slope ones here were constrained to like 0, 1, 2, 3. So we're not, those are all constrained, so I don't need to count those, right? So I've got, what have I got? 7, right? So I've got 7 parameters in the variance covariance side. And I said here, right, that I have 4 times 5 divided by 2 is 10. So I have 10 knowns. So for that model with 4 time points, I've got 10 minus 7 equals 3 degrees of freedom in the, in the variance covariance part, right? Plus 2 degrees of freedom, because it was 4 minus 2, 2 degrees of freedom in the mean intercept part of the model. And so if I run this in Mplus is going to tell me that I have 5 degrees of freedom. Mplus is going to say 5 degrees of freedom. It's not going to say 5 degrees of freedom, parenthetically, by the way, 3 of them are from the variance covariance side, 2 of them are from the mean side. I want you to know that. You need to know that. But Mplus is not going to make that distinction overtly for you. Like, everything in the output would point you in that direction if you understand it, but it's not going to, like, in bright flashing letters point out, like, hey, that's where the degrees of freedom are coming from here, right? And if you think about a model where, we only have 3 time points. If I only have 3 time points, I could estimate 3 error variances, right? Horrible pen. So 3 time points. I estimate 3 error variances. I estimate a factor variance for the intercept. I estimate a factor variance for the slope, right? And I still estimate a covariance. And so actually with 3 time points, I've got 6 parameters, right? Not that different from over here where I had 7 parameters in the variance covariance side. And with 3 time points, think about that. How many knowns in the variance part? Well, 6, exactly. So I've got 6 parameters I'm estimating. And I've got 6 knowns, right? So 6 minus 6 equals 0. So when you have a standard latent growth curve model with 3 time points, you're actually just identified in the variance covariance side. You have 3 mean pieces of information, right? Minus 2 mean parameters you're estimating. So you have 1 DF. So for a latent variable model, where you only have 3 time points, that model is, first of all, a 1 DF model. So remember how I said we got to be careful of our SEA with really low DF models? Well, this is an example of a really low DF model because it's only got 1 DF. And second, that 1 DF is coming from the mean structure side. So what that's telling you is if the model fit is lousy, it has nothing to do with the variance covariance side of the what's going on. What it's telling you is that you're doing a lousy job reproducing the means at those 3 time points with the two latent variable means parameters that you're estimating. That's where the misfit is coming from. Does that make sense? Yeah.
Can you clarify what is the mean side versus the variance covariance side of the model?
The mean side is I've got means, right? I've got means for my variables. Those are the knowns. And on the unknown side, it's any means and intercepts that I'm freely estimating. So just like when we're counting parameters, you can sort of count them all up together, right? I mean, that's, again, Mplus is going to do that. It's going to say there's 1 DF, and that's true. There is 1 DF. But I think it's very helpful for you to understand and think about where do those degrees of freedom come from. And what I'm saying is, like, in the variance covariance part of the equation, like if I had just shown you this model, let me show the picture. Where have I got a nice picture? Somewhere I've got a picture. Ah, there we go. So if, oh, well, except for that, let me just change these to be 0, 1, and 2. So it's really clear that these are constrained, right? If I show you this picture and I had asked you to count before we started talking about means and intercepts, if I asked you to count the number of degrees of freedom, you would have been like, oh, 3 error variances, right? 2 variances, 1 covariance, and I've got 3 times 4 divided by 2 pieces of information. 6 minus 6 is 0, and you would have said this is a just identified model. And it is in the variance covariance structure. But, like, what we're really interested in, because we're looking at growth, so we're looking at change, so we need means, right? You want to know about change and growth, you need to be thinking about means. You need to be thinking, not just about variances and covariances, but also about, like, means. And so on the mean side of the model, I have 3 means. I have the 3 means for Piot, because I have the 3 Piot means, right? But I'm going to estimate a mean for this, and I'm going to estimate a mean for that. And so I've got 2 latent variable means that I'm estimating. And the 3 minus 2 gives me the 1 degree of freedom, and that 1 degree of freedom is coming from the mean structure, not from the variance covariance structure. So a really cheaty way, don't do this by the way, but a really cheaty way to get this model to fit would be to freely estimate any one of these 3 intercepts, right? Because if you did that, you would eat up that last degree of freedom, and so the model would fit perfectly, and you'd get a 0 DF model. You get a chi-square of 0 with 0 DF. I don't even tell you nothing, but, I don't know, you get parameter estimates, but I don't know, it would be a silly thing to do, but the point there is, like, that's, right, you only have 3 pieces of information about means. You've eaten up 2 of them here. You're constraining all of these to be 0. And it's because these 3 are constrained to be 0, you use 2 up here, but that leaves 1 left for you to have as a degree of freedom. Yeah? Maybe? Kind of? Seems like a good time for a break. Yeah? Okay, so we'll just let it all, like, gel in your heads for the next. Let's come back at 11:15. Take a 10-minute break. We'll start promptly at 11:15. And that gives us an hour to do everything else. All right. Yes.
Question.
Sure.
If instead of having 3 time points, the person have more than 3 time points.
Well, then obviously this is going to change, right? You have more than 3 time points. You're going to get degrees of freedom in the variance covariance part.
I was wondering if we can create like a just identified model for the variance covariance part of the model to evaluate the set of the mean part of the model. Can we do such a thing?
Well, yeah. I mean, in some sense, can you? Yeah. Should you? I don't know if you should, but I mean, in some sense, that's a little bit what you're doing. When you think about it, when I gave that example of allowing those 2-factor limits to really vary, right? Because where were we on? How many degrees of, now I forget how many degrees of freedom we had.
I'm just.
5, I think.
3, 2, 3, did we have 3?
Yeah.
Yeah, it was 7, that's right. So it's 10 minus 7. So, I mean, so there you're down to 1 DF. You're not actually just identified, but you could come up with something else. I wouldn't necessarily like suggest that per se, although there are some cheaty ways to do that actually too, because like it turns out that if you fit we really didn't talk too much about like the error variances being constrained to be equal across time or not, like for that, we've just been counting them as freely varying. But in multi-level, you actually only estimate one pool error, residual, variance. So, but it turns out like if you fit, for example, if you have 4 time points and you fit a quadratic model, and you allow all of the errors to freely vary, I think this is true, then you have a just identified structure in the variance covariance part. Because you pick up you pick up additional parameters that you're estimating because you have the variance of the quadratic plus you have the covariance of the quadratic with the linear and with the intercept, right? And if you allow all of the error variances to be freely estimated, then actually what you get in that situation is a variance covariance model that is just identified. And again, in that scenario, then any of the misfit is coming from the mean side, and it's going to should be like a 1DF model. So, yeah. But I mean, I don't know that I would say as a general rule that that's necessarily what you want to do. Sure.
What did that?
The one that's like right on the ground floor.
We don't we have our box in it? No, we're like all of our desks.
Oh, where our desks are?
Yeah.
001.
Is it like,
Yeah, you're. I thought you meant
is that what it says like
like
on the, is that what it says on the outside?
Yeah.
It's like, oh my God,
I mean, it should, Melissa.
I'm just trying to tell a stupid word to something. Oh. I don't know what happened with this.
I'm like
It's like
90%
0,
sure it's
0
001.
something, I know.
Yeah.
Okay. I'll just tell her, I think it's 0, 0. Go. Thank you. Thank you.
I'm sorry, Nina.
Well, actually, if there's an extra one there at the end of any of the rows, let me know, because I just realized I gave them all away.
Missing one.
What, you're missing one?
Yeah.
Oh. You have an extra? I'll make it. There you go. Okay, you did pretty well there. That. Go print one more.
No differences.
I know, I panicked. Okay, so it's not that. No. It's getting this page.
All right, so let's talk about a couple more things before we do our Mplus example. So I skipped over a couple slides. I think they will go pretty quickly, and then I want to make sure that we get to our Mplus stuff. So just a couple of things to think about. Not all fit indices are necessarily available for models with mean structures, nor do they necessarily all make sense. And, just as if you think about, for example, the incremental fit indices, which really are sort of saying, where are you, sort of on a continuum from the worst possible model to the best possible model. Remember, we said the worst possible model was like, oh, I'm estimating variances, but I'm not estimating any covariances. But what do you do with the mean structure part? What's like the worst possible model in terms of the mean structure part? Actually, when this is dating me, but like when Amos, this is like 20 years ago now, first came out with sort of mean structure stuff. All of the CFI and the TLI were computed, and they were super problematic because all of the baseline models were computed with the baseline model assumed that all of the means were 0, which is like, does that make sense? Probably doesn't make sense. But then, of course, if you do the means are freely estimated the way that you would do the variances being freely estimated, then that means that, like, take a growth curve model as an example, then the growth curve model would have worse fit than the baseline model, right? So there's this, what is the right baseline model? What's the right independence model for mean structures? That's again, an interesting question. All right. So this is, I think we've kind of hit this, but right. So for both the slope and the intercept, the latent variables, there's a mean and a variance. The mean of the intercept, if we've centered it, which we haven't even really talked about centering, but we center it so that 0 is the starting point, then that mean of the intercept is telling me where does the average person start? What's the expected start value? Slope is what's the average rate of change? And the variance in the intercept says how much do people differ from each other in terms of where they start? And the slope variance is telling me how much do people differ from each other in terms of their rates of change. So that is really, and these 4 parameters in the latent variable, the parameters that deal with the latent variables in these latent growth models are the most interesting. Then there's also the covariance between the slope and the intercept. Oh, I should say too, that when we're looking at growth curve models, you want to look at the unstandardized estimates for everything except for the correlation. So you want to look at the unstandardized estimates for the slope and intercept means, the slope and intercept variances, right? Error variances you're not really going to do much with, but all of the parameters you're interested in looking at and reporting come from the unstandardized parameter estimates, except for the covariance between the slope and the intercept, because of course covariances are really hard to interpret, right? Because they're in the metric of whatever those 2 variables are. So that's the one place where you're going to go to the standardized parameter estimates and report the correlation between the slope and the intercept, because that's just way easier for people to understand than a covariance, right? And the correlation, so correlation is just the standardized covariance, and it's just telling you like what's the relationship between the slope and the intercept. And again, if we code things or center things so that the latent intercept is where people start, then that correlation between the slope and the intercept is telling us what's the relationship between where people start and how fast they grow. And again, if you're a developmentalist, that's super interesting, right? And a positive correlation would say, okay, people who start higher, they grow faster. Actually, I have a picture of this, so let me. Okay, so here we go. So if you have a positive slope, right? You have a positive slope and you have a positive correlation between the slope and the intercept, then that's saying that people who start higher, so they have higher intercepts, have more positive slopes. So they start higher, they grow faster. People with lower intercepts have less positive slopes. So anytime you have a positive correlation, you're going to get kind of this fan-shaped pattern, okay? So the top shows you positive slope, positive correlation. Now you're also going to get a fan-shaped pattern if you have a negative slope and a positive correlation. But it's, so what it's really saying there is that, again, and this is where people sometimes get tripped up, it's still saying people with higher intercepts have more positive slopes. It's just that the slope is negative now. So having a more positive slope actually means it's less steep. It's like less negatively steep, right? So like over here, if you've got a positive slope and a positive correlation, like the higher people, right, are growing faster. Over here, what we're saying is people who start higher are declining more slowly, right? Which is, depending on what you're measuring, right, that, that can be, right, these could be good or bad things. But so higher intercepts have more positive slopes, but here, because the slope is negative, it's more positive also means less negative. It could actually, if we got positive enough, could become positive, right? But does that make sense? And then same kind of idea for the negative correlation between the slope and the intercept. If you have a positive slope, then a negative correlation between the slope and the intercept means the slope is more negative, less positive, right? More negative for those with higher intercepts. So people who start higher are growing more slowly over time. And if the slope is negative and you have a negative correlation between the slope and the intercept, then that means that the slope is more negative for those with higher intercepts. So they are declining faster. So in both cases, the negative correlation between the slope and the intercept is giving you what's sometimes called like a pincher pattern, right? Because people are actually getting more similar to each other at the sort of end than they are at the beginning. But again, what we're really saying is, you really have to interpret, I guess what I'm trying to say is, when you see the sign of the correlation between the slope and the intercept, to really make that interpretation of what it means, you also really need to think about what the sign of the slope itself is, right? And that's why I've given you these slides. So you can just go back and refer to these slides. Okay. I'm going to skip that slide. I'm going to skip that slide. We already did those slides, clearly. Oh, one thing I do want to say here is, you'll see I don't always do this because, well, A, I'm lazy and I take other people's graphics a lot, but B, even when I draw my own graphics, I don't usually draw the triangles, but you will see in SEM, some people do this and some people don't. So if you see triangles in a path diagram model, the triangle represents means. So sometimes people will not put the triangles in and they'll just, like I wasn't putting the triangles in and I was just saying, we're estimating a mean and we're estimating a variance. But people said like, hey, how can we make sure that people understand that we're estimating means here? And so when when I first saw this, it's grown on me. When I first saw it, I really hated it. So, but what this is saying is like, okay, right? I'm here. This is actually the parameter for the mean of the intercept, right? And this is the parameter for the mean of the slope. And if I actually were going to estimate an intercept down here, then I would actually draw a path from, from this little triangular one, and I would draw it to, but I'm not doing that. But that's what this means. That just is telling you where you're actually estimating means and intercepts. So that's all that triangle means, and then it's just sort of a way to sort of designate the parameters that you're estimating. So I wanted to make sure to kind of explain that to you so it doesn't throw you for a loop.
Is that always a triangle with one in it?
Yeah. And it makes sense because if you think about it, again, remember, like, we're generally, with the intercepts, right, we're like here, minus, these are ones. And it's just generally, like it's the sort of like the intercept for the, it's like the intercept for the mean, it's like the intercept for the latent variable mean and the intercept for the latent variable slope. So yeah, it's always going to have a 1 in it. Okay. We already talked about what variables we are estimating. We haven't talked about constraining the error variances across the time points to be equal, but we could constrain the error variances. I was counting that we're actually estimating an error variance for each of our time points. That means that the measurement error can actually be different across time. There could be more measurement error as we go along in time. So that allows us to that allows us to account for that heteroskedasticity that we were sort of talking about. But if you don't think that's an issue, or you can test that actually, and you can theoretically constrain the error variances to be equal across time. And so then you're just estimating, then you're saying there's the same amount of measurement error across each of the time points, right? Like there's the residual variance at time 1. So sort of those residuals that are the difference between the model predicted and the actual scores, that residual variance at time 1 should be the same as the residual variance at time 2, should be the same as the residual variance at time 3. And so I can constrain all of those error variances to be equal. And what that will give you is something that is akin to a standard multi-level model, where in the standard multi-level model, you estimate a sigma squared, which is your pooled residual, is your pooled level 1 variance. So, I would say that in general, the standard SEM model actually doesn't constrain the error variances to be equal. The more common starting place allows those error variances to vary across time. But the standard multi-level model, and again, you can there are ways to be more flexible in the multi-level framework too, but the standard multi-level model does constrain those error variances to be equal across time. So like if you just sort of run a standard SEM growth model and a standard multi-level growth model and just sort of use the defaults that are given and not think about it too much, you might find you don't get the same thing. You don't actually have the same number of parameters or degrees of freedom. You don't get the exact same parameter estimates, and that is likely why. I mean, another reason is the estimation technique you're using might be different as well. So you might, but generally speaking, if you fit the same model in multi-level and an SEM framework, you should, within sort of rounding error, if you fit the model the same way, get basically the same thing. Yes.
So by setting the residuals one, is that equal, or would that have to be like correlate residuals and set those correlations?
No, you would actually you would constrain the variances of the residuals to be equal across time. So I have an example of that in Mplus, but basically, like, remember to say something about the variances of the residuals.
And that's not shown, right? That's that like little double arrow that you're not actually showing us on the.
Oh, well, yeah, like
that's what you're right.
Yeah.
Okay. That helps me.
Thank you. I was like, oh,
Sorry. Yeah, right. Like, here we go. All of these things have variances, right? And so right now we're not constraining these to be equal. If I wanted to constrain those to be equal, what I'm saying is the variance of error 1 equals the variance of error 2 equals the variance of error 3. And to do that in Mplus, I can just, in my model statement, say, what are the names of my variables? P-1, because remember it's referring to the error, right? So P-1, P-2, P-3, and then here I can I could give a number or a letter. I could be like EV, let's say, or error variance. And once I do that, I'm actually telling Mplus, oh, constrain all of those error variances to be equal to each other, right? Because I'm basically saying I'm estimating one parameter for each of these, the same parameter, right? Does that make sense? So I can do that, and that's what I would do if I wanted to actually reproduce the standard multi-level model. I need to do that to reproduce the standard multi-level model. Okay.
We're not using that code.
Not right now, but we will. I mean, I think I've got to get through this. I'll show it to you both ways. But like the baseline usually allows them to freely vary. Yeah. Okay. As I said, we're not estimating intercepts for those endogenous indicators. They're all constrained to be 0. Oops, hold on. And we're not estimating any factor loadings for either factor in the standard latent growth curve model. Okay. And okay, I think there's nothing new there, but what I do want to talk about briefly is that, again, we need to think about how we code or center time so that we have a meaningful 0 so that the intercept is interpretable, right? Because remember, the intercept is the predicted value when the slope factor is 0. So so I'm talking about this intercept, right? This, again, the action in this model, the most interesting action is really happening here, sort of in the structural part of the model. And if I want to think about how do I code time here, and I was giving the example of 0, 1, 2 is really common. If I do that, then the intercept is the predicted value on, the predicted value when time is 0, and time is 0 at the first wave of data collection, right? So it's really important to think about where you want that 0 to be and to have a 0. So for example, if you have ages, let's say I said we've got P out here, and we've got ages 6, 8, and 10. So if I put in 6, 8, and 10, they're all fixed, but then what's my intercept? My intercept would be the predicted value of, like, it would be the predicted PIAT score at age 0, right? Well, what will be the predicted PIAT score at age 0? Actually, it won't be 0 because it's a linear model. So we'll actually extrapolate. It'll be something negative, I would predict. But, anyway, that would be dumb, though, right? We don't, I mean, that's throwing away perfectly good parameters because we don't actually care we know what kids' reading scores are at age 0. So we don't want that. But what I could do, right, is even though I've got them at ages 6, 8, and 10, I can center by just subtracting 6 off, right? And then I get 0, 2, and 4, for example, and I could put 0, 2, and 4 here. So now 0, 2, and 4, so my intercept is going to be like this predicted score at age 6. That makes sense. At the start of the study, which is when kids are generally age 6, what's my slope now? Because the slope is always the unit change in the outcome variable per unit change in the independent variable, right? So if this is how old kids are in years, right? If I've got 0, 2, and 4, because I've measured kids at ages 6, 8, and 10, what's my slope going to give me?
Every 2 years.
Well, it's not going to give me every 2 years because I've made it 0, 2, and 4. So it's going to be the change in the outcome per 1 unit change in time. Because I've coded it this way, I'm going to get sort of this approximate average yearly growth slope. But you are right that if I do this, I can make you right. If I make it 0, 1, 2, right, then what a 1 unit change is going to be a change for every 2, like it's going to be the average growth over a 2-year time point, a time lag, right? So you also want to think about how you're kind of setting up your time variable to be what it is you want it to be. So like whether you use 0, 2, and 4 or 0, 1, and 2, those models are actually, they're going to be statistically equivalent. They're going to have the same fit. They're going to have the same intercept, right? Because they're both centered at 0. The slope for this one is going to be twice as big as the slope for this one, right? So, I mean, either one is fine. Just make sure you know what you're doing and that you interpret accordingly. I personally prefer the 0, 2, 4 because I just think it's easier to talk about, like a yearly slope versus a bi-yearly or even that, like semi-yearly, bi-yearly, whatever. So you get the idea. So, and don't throw away those intercept parameters. So think through where you want, how you're going to center time to make the most of those parameters, right? And for linear models, the choice of centering is going to affect some but not all of the parameter estimates, but it is going to give you statistically equivalent models. So for example, I'll let you think about what parameters are going to be affected and which aren't, because I think that's a question I asked you in your homework. So, where time is 0, that's really where you're centering time. Most commonly, it's at the baseline or the first time point. But sometimes in intervention studies, people like to center time at the end because they want to see, like, how, especially if you've got like a treatment and a control, and you want to know how different were people at the end, right? So maybe you want to center time at the end. Or you want to center in the middle? Maybe centering at the middle, yeah.
Usually it's more precise values in the middle, right?
Yeah, there could be a case to be made for centering in the middle as well. So yeah, I mean, I think yes, any of these, and actually there's like quite a bit of literature on should you center at the end or should you center in the middle? Should you use orthogonal polynomial contrast codes? Blah blah blah. Anyway. So different centering choices are going to give you the same model fit, same, same slope mean and variance and same error variances, but they're going to give you different means and variances for the intercept and a different slope intercept covariance, which is going to give you a different slope intercept correlation. And so actually, I would argue that one of the most important considerations for applied researchers about where to center is where do you want that, where do you want that correlation between the slope and the intercept to be? Do you want to be able to talk about the correlation between where people start and how fast they grow, or how fast they grow and where they end, or how fast they grow and where they are in the middle, right? So that actually is a very important consideration. All right. In terms of data, obviously we can use raw data. If we use a covariance matrix, we have to also report means because, I mean, that's kind of obvious, right? Okay. And so for this example that we're going to do, it's this PIAT data. So we only have data across 3 time points where kids are approximately 6, 8, and 10 years old. And these are actually a few of the kids in the data set. And these are like little individual growth trajectories. And again, you can see that kids definitely start sort of at, most kids are starting kind of low, but looks like there's some variability. Like look at number 17 there. That person's definitely starting a bit higher, but then actually going down across time. Most kids seem to be increasing across time, but there's a lot of variability in how much they're increasing across time. So, this kind of, good thing about looking at these is it also kind of gives you a flavor of what you expect to see in terms of your output. So you can kind of, I look at this and I say, okay, the slope should be positive, right? There should be a fair amount of variability around the slope. The intercept should be, I don't know, fairly low. If it's probably going to be somewhere around 20-ish, right? I think is, or a little lower than 20 or something. And it's, there's going to be some variability there too. I mean, I don't know what the exact numbers are from looking at this, but it gives me sort of a flavor. How are we going to code this in Mplus? Well, Mplus has this super shortcut code for latent growth models, which is great. So you could longhand it and set it up just the way it looks with the factors, blah, blah, blah. But it's way easier to use the super shortcut code. So I give a name for my latent intercept and I give a name for my latent slope. So that's what I'm calling I and S here. You can call those whatever you want. You can call it intercept and slope. You can call it factor 1 and factor 2. Whatever. You can give it whatever name you want. But what's important is you're going to then use, what's the name of this bar?
Vertical line.
The vertical, there's a name for it. Anyway. You're going to use the vertical line. There's an actual name and typing for it. You use the vertical line here. So you're saying, right, you say, I got an intercept, I got a slope, or I've got a randomly varying, really what you're saying is, you got a randomly varying intercept, a randomly varying slope, and you'll see actually this sort of indicates when we've got random stuff going on in Mplus. And then here is where I'm actually giving the information about the slope coefficients, which are what's getting plugged in here, the B1, B2, B3. So if I want it to be 0, 1, 2, I'm going to put P.1 at 0, P.2 at 1, P.3 at 2. Okay, now, and remember, that's now going to give me a slope for every 2 years of growth because we've got the scores at 6, 8, and 10. If I wanted it for yearly, I would just go at 0, at 2, and at 4. Okay? And by default, Mplus is going to freely estimate these variances. Okay? So that's it. You don't have to say like the intercept is at 1 across all the time. It knows that. It knows this is the intercept. It knows to constrain all the factor loadings for the intercept to be 1 across time. So you don't need to say any of that.
This is a quick question.
Uh-huh.
If we are going to center at the end, then the other 2 ones are -1.
Yeah, that's right.
-2 and -1.
Yeah, if you're going to center at the final time point, and I think I have an example of that somewhere, but if you wanted to center at the final time point, you would go at -4, at -2, at 0, or you could do at -2, at -1, and at 0, depending on whether you want it yearly or bi-yearly, right? but like whatever, you always want time to be going up. So if you're centering, before, whatever's before the 0 point is going to be negative, and whatever is after this 0 point is going to be positive. Good point. If I want to constrain the error variances to be equal, I showed you this earlier, I can just say P out 1, 2, 3, and then whatever I put in parentheses, it could be a number or a letter or a word, but I'm telling it to constrain all three of those to be equal. Okay, now this is, I won't spend too much time on this because I want to make sure we get time to do the thing, but I can set up plots so I can actually see my growth curves. So to do that in the plot command, say type equals plot 3, and then you can either do like, for example, this, if you do this, y1, 0, y2, 1, y3, 2, y4, 3, you're telling it that's what I want on the x-axis. So for example, in our example with PIOT, maybe I'd want to say like, that the PIOT 1 is that I have that at 0. I could go 0, 2, and 4, for example, or I could go 0, 1, 2, whatever I like. Okay. Or you can just put a like asterisk thing, and then it'll generally figure out what it should be. There are ways you can actually do multiple growth processes. I'm not going to talk about that right now, but we can come back to that at some point. You can also define new variables in Mplus pretty easily. And this comes in handy when you're centering stuff. Hold on. Can I move that? All right, there we go. So in the define command, so you can say define colon. And for example, if you wanted to create a new variable that's the mean of a set of variables, you can go mean expo equals mean of all of these exposure variables. And that would actually define a new variable that's the mean of these 5 variables. And then if you wanted a variable that was like mean centered, for example, then you could say, expo, like now I'm calling this a new variable, expo PC0 is exposure 0 minus the mean of exposure. So now I've just created the deviation between this exposure and the mean across time. Or again, it could be cross people, but whatever, you can do however you want. And then, if you want to do something like, if you want to just quickly do it for all 5 variables, you could say like do from 0 to 4. So I could have expo PC number sign, so it's going to replace that from like 0, 1, 2, 3, 4, right? So it's like a looping thing. Is going to be expo, again, it's going to go in order, 0, 1, 2, 3, 4, minus mean expo. And then this one line would actually create all 5 of those variables. That would be deviations from that mean exposure. So that's one way you can divide. I mean, you can, and there, this is just one example of how you can do stuff. You can also center variables. There's a center command. So I can say center, and I can say center these variables, and then in parentheses grand mean, and it will grand mean center those variables. I could actually say center a variable around the group mean, and it will group mean center those variables. Or I can say standardize, and of course the standardized variable is going to be like a z-score variable where it has like a mean of 1, mean of 0, standard deviation of 1. So, and of course, these would all, there we go. So these are all options for how you can actually transform things right in Mplus. Yes?
What's the use of these new variables? I mean, what do they represent?
Well, I mean, so the centered variables are just centered variables, right? When might you want to center a variable in like a growth model? I didn't say this, but for example, we haven't gotten to this yet, but what if you want to have an independent variable predict the latent mean and the latent growth slope, right? So in that case, you would, if the variable is not already standardized, you would want to center that variable so that what you get is now going to be more interpretable, right? So it's going to be like the latent mean on average rather than the latent mean when this variable equals 0, which might not even make sense, right? So, like for example, if you had SAT predicting the growth intercept and slope, and you don't center it, then, you know, now suddenly, let me do it this way. Here. Okay, so here's what I'm talking about. You've got your intercept, you've got your slope. But imagine now you have SES or SAT or something predicting your intercept and predicting your slope. So now these are no longer exogenous variables. They're now endogenous variables. So now we're not estimating a mean for the intercept and a mean for a slope. I'm estimating the intercept for this latent intercept and the intercept for this latent slope. And the intercept is going to be the predicted value on the intercept when this thing is equal to 0. So now I just saying logic, but just sort of going up the chain, I need to make sure that I can, like, that's going to be interpretable, right? So when you have time invariant covariates that are continuous, you're generally going to want to do some sort of centering or standardizing or something so that you actually get something interpretable. So that's when you would use centering. And then, well, this example is just creating like a mean exposure score across time. And then this is actually like the difference between your score at time 1 and your average score. So again, you could imagine for studies that might actually be useful to be thinking about, like, how much is the person's score deviating from their overall score. So that's like a person mean-centered score, which is the same as like a group mean-centered score in multi-level modeling. Okay. I don't want to say anything about that because we haven't run the model yet. So now, do not want that ink annotation. Let's go to our models. Oh, can you, I think we were short like 1 or 2 of the things. I sent them downstairs. Can you go pick up the output? I think there should be 2 down there. I meant to tell you that right away, but I totally forgot. Okay, so now let's go to Mplus. Let me move this.
Do the rules apply the same around sample size with 200 models?
I mean, yeah. I mean, that's all, like, all the rules are made up, right? But,
You need more.
well, no. I mean, the thing is, like, with growth models, you might be able to get away with less, actually, because you have, it's a very simple model. You're not actually estimating a lot of parameters. You don't have a lot of degrees of freedom, right? You can probably, if it's a simple linear growth model like this, you could probably get away with less than 200 people. So yeah, but I mean, you know, it shouldn't be like 20 either, you know? Okay. So let's go to Mplus, and it's, if you go into the week 7 folder, you should find everything you need. Let me open up Mplus here. Open. Let's see, desktop. So I've got my week 7 folder on the desktop, and let me open up model 1. So this is that PIAT data that I've been talking about. So here I've got, you know, again, it's a wide data file. So the scores across the 3 time points are variables. They're not, you know, it's not in a long format the way you would have in multi-level modeling. Here are the names of the variables. So I've got an ID variable, LD fake, which is going to be our exogenous variable, and then I've got some different age variables that we're actually not going to use right now. So for our first model, we're just going to use PIAT 1, 2, and 3, and again, these are measured at 6, 8, and 10 years old. And you can see the model, I'm calling it intercept and slope, and here I've coded it so it's 0, 1, 2, which means that my growth slope is going to be it's going to be the change for a 2-year time span. Okay. Here's my plot command. So you can see I'm saying, I always say plot 1, 2, 3, but you don't need to do that because if you say plot 3, you get plot 1 and 2. So you can just say type equals plot 3. And then series, I've got PIAT 1 is 0, PIAT 2 is 1, and PIAT 3 is 2. And then finally, I didn't talk about this, but the save data command will save out factor scores in case you want to actually look at what people's estimated intercepts and estimated slopes are, which can be really interesting. All right, so, and you can see I said up here, our error variances are not constrained to be equal to each other because by default they're not. So we run this model. This is 8.6. I didn't realize that. I need one. Maybe nobody else does, but I need one. All right, thanks.
Yeah.
Oh, sorry. Oh, okay. Well, now I'm flush with these. Okay. So if you look at your output, and I can bring it up on here. Let's talk about what we've got and make sure we can interpret it. Oh, by the way, look at how crappy my RMSEA is. 0.232. That does not look good, does it? Okay. So, let me get this. Output. View. No. Edit. Change font. Choose font. I want it big, right? Okay. Okay. There we go. Okay. So let's see here. So you can see I only have 1 degree of freedom here, and my chi-square is 5.8 with 1 degree of freedom. And that 1 degree of freedom is coming from the mean structure of the model, remember? We talked about that. Okay. RMSEA looks horrible because I have 1 degree of freedom. Actually, my CFI and TLI, they don't look that great either. Now, let's look at our model results. So here we go. Mean of the intercept is 20.76. So what is that? Oh, if you look on the output, what are you right now? Where am I right now?
Yeah, one thing.
Oh, on the output, I'm on page 3.
Thank you.
So output page 3.
Thank you.
Look at you've got the means, 20.76. Where is it? 20.746, sorry. Okay, so what does that mean? That means that is the intercept. So that's the predicted reading score when kids are 6, right? Predicted reading score when age or time or whatever is 0. And in this case, that's at age 6. So at wave 1, which is when most kids are around 6 years old, the expected reading score is about 20.75, let's call it. We're going to round to 2 decimal places on this stuff, okay? And let's call it 10.09, right, is the model predicted slope. So that's saying, remember, for every 1 unit change in time, which in this case is 2 years, I expect kids to grow by about 10.09 units. So if I were to rerun this and recode that to be 0.24, I would expect that slope to actually literally get cut in half to be a yearly growth slope. And that's how it'll work out. So I could do that and say like, oh, okay, 10.09 points per wave is actually going to give me 5.05, basically, a slope of about 5.05 points increase per year. Okay? And the variances in the intercept and the slope, that's telling me about how much variability is there in terms of where kids start, and that variance is like 25.32. I could take the square root of that, and that would give me an idea. I think that's really useful, actually. You know, if you say like, okay, the intercept is what I say it is 20.75, right? But I would expect 68% of kids' scores to be plus or minus, let's just call this the square root of 25, right? We're pretty close. Square root of 25 is 5, right? So on average, kids start out at about 20.75. About 68% of kids should be between 15.75 and 25.75, right? So that's like a 68%. This isn't a confidence interval, right? Because this has nothing to do with standard errors. It's the standard deviation, you know, of this estimate. So it's like about 60, I would expect 68% of the sample to have starting scores between 15.75 and 25.75. And I could say, 95, I'd expect about 95% to be between 10.75 and 30.75 in terms of their reading scores at age 6. So that's useful to know, because like on average, on average, people are starting out around 20, but there's actually a lot of variability. So about 95% of the sample, somewhere between around 10 and 30, right? So that kind of gives you an idea about the variability. And I can do the same thing with the slope. So the slope was, again, it's a bi-yearly slope. So the slope was around 10.09 for every 2 years, right? And the variance around that was 27.559. So now I could go 10.09 plus or minus, my math broke.
I think I do have a spare math.
I might actually, do I have my, I probably do. Hold on, let me see. I usually have spares. Problems. Let me see. I might not though. I might need yours, actually. I know I have spares in my book bag, but I don't think I have them in my purse. Welcome to 2022. All right. Woo-hoo, thank you. Okay, much better. So now I have 10.09 plus or minus, I don't know. Let's call it 5.3. Oh, square root of 27 point. We'll call it square root of 27.56, right? So I can do the same thing and say like, the average slope for the average 2-year slope is like 10.09, but again, this is going to be something a little bit bigger than 5. So if you think about that, that means that 68% are going to fall within something just under 0, right? Because this is going to be a little bit bigger than, just under 5, sorry. 95% is going to be just under 0. So we're going to get something that's like, again, I'm just going to round it and say, 68% are going to be somewhere around 5 to 15, right? And 95% of the slopes are going to be somewhere between, it's going to be a little less than 0 actually, to, again, a little bit bigger than 20. And this is kind of useful too, because then you get this idea of this distribution of slopes and you're thinking to yourself, okay, so like on average, the slope is, kids are increasing by about 10 points every 2 years. And most kids are going to be positive. When you could create this little interval though, you'll see that there are kids at the tail who are actually going to have predicted slopes that are negative, which makes sense given what we saw in the sample too, right? All right, so our residual variances, remember we allowed those to vary across time. And you can see actually the residual variances for times 1 and 3 are actually really pretty small. They're not statistically significantly different from 0. But the residual variance at time 2 is considerably larger, and it is statistically significantly different from 0. So when I look at those, I think, oh, well, if I constrain those to be equal, it will, I would expect that to worsen the fit of the model, right? They don't really look like they're equal. In some sense, looks like maybe the residuals for time 1 and 3 could maybe constrain to be equal, but the residual for time 2 looks different, right? Which is weird. Don't ask me why that is. I don't really have a good coherent conceptual reason for that off the top of my head. And then, so this is all coming from the unstandardized estimates. Here's the slope intercept covariance. It's negative. It's going to be, so the correlation is going to be negative. So that, remember, that means that kids with higher starting scores are going to grow more slowly than kids with lower starting scores. But like, to really interpret this, this is the one place where we're going to go to the standardized solution so that we can actually get something that's more interpretable than -7, right? What does that mean? I don't know. But here, what I see is that the correlation between the slope and the intercept is -0.27, right? So it's not that strong. And it's also actually not statistically significantly different from 0 in this case. It's 0.07. So like there's, there's a slightly negative correlation between where kids start and how fast they grow, but that correlation isn't actually statistically significantly different from zeros, and it's not very big. And frankly, this is a parameter that is often sort of more noisily estimated than some of the other parameters in the model. So, you know, and so there are times with these kinds of models where sometimes you can see a slope, covariance between the slope and the intercept that looks really large, but then the standard error is so large that it's not statistically significant. So it is really good to look at the statistical significance and not to like overinterpret this, you know, if it's not statistically significant, because often they're just that particular parameter is often very noisy. Like I've run models where the covariance between, or the correlation between the slope and the intercept is like 0.95, and it's not statistically significantly different from zero. So like, if you only looked at the number, you'd be like, oh my gosh, that's huge. But then the standard error is so huge that like, you know, you really can't. So in that case, like I can't really say much about the covariance between the slope and the intercept if that's what's going on, because I just don't have the precision to really say much. All right, so that's the first model. I don't think, oh, hey, let's look at our plots. Let's see here. Sample, let's look at our sample and estimated means. Okay, view. Okay, I can move that. So it's not the prettiest plot. I wouldn't use it for any publications or anything, but you can see here that I've got like, you know, it's mapping out what are the sample means, and those are, yeah? Oh, so sorry, yeah. So, well, first you got to put in the plot command, and then when you're in the output, you just click on this little graph. And then when that comes up, it gives you all kinds of different plots you might want to see. So I said sample and estimated means because I always like to see those in combination. And again, we only have 3 time points, so like, you know. But what you can see is, and this explains why hard. If you look at this, you can kind of visually see why the residual variance at time 2 is bigger than the residual variance at time 1 and 3, right? Because look, my sample means and my model predicted means at time 1 and 3 are basically identical, right? But they're not here. And they're not here because, probably because it's not like completely, right? It's not completely linear. It's like a little non-linear, but whatever. We can't do anything about it. We only have 3 time points. But, you know, okay, that doesn't look too bad. It's not a very, I mean, it's not the most interesting graph here, but that's how you get those graphs. So now, how are we doing? Okay. Now, what if I wanted to, what do I want to do? What if I wanted to constrain the error variances to be equal? Okay. Maybe I'm going to skip that one because you know how to do that, right? You know, it's not that interesting and it doesn't fit as well. If you look at model 1B, you'll see that when I constrain the error variances to be equal, the chi-square goes up to 13.48 with 3 degrees of freedom. I can do a chi-square difference test, and the chi-square goes up by 7.67 with 2 degrees of freedom, which is statistically significant. So it's a worse fitting model, and again, not super surprising given what we saw. So let's go to model 2, though, because this is the one that actually has a predictor in it. So this is important. Now things are going to change. I mean, well, so let's go to open model 2. So this is what I'm talking about. Ooh, okay, it's not going to be SES, but what we've got now is I've got a variable called LD fake, and it's called LD fake because it's a totally fake variable that I cherry picked so that I would get really like dramatic results in this example. But please do not assume that it says anything about any real kids because it's totally fabricated, not simulated, just totally cherry picked for pedagogical reasons. So we got this whole thing going down on this part of the model, but really what I'm interested now in is heck, okay, I saw there's a lot of variability between kids in terms of where they start, and I saw there's a lot of variability between kids in terms of how fast they grow. And I want to know, does knowing if the kid is diagnosed with a learning disability, does that help to predict the between student variance in terms of where kids start and also in terms of how fast they grow, right? Or right? Because we're two different things. And so now that means that this latent intercept is an intercept and not a mean, right? So we really do have now, what we're going to have is like a disturbance for this intercept, and we're going to have a disturbance for this slope, right? And this is really the unexplained variance after accounting for this LD variable. And this is going to be the unexplained variance over here after accounting for the LD variable. And this is where I was saying you really want to think about how do you code and how do you interpret the LD variable. So now this is a 0, 1 variable. So I don't have to center it, but I do have to be cognizant of how I interpret it. So if it's 0, in this case, it's 0 means no, not diagnosed with a learning disability. 1 means diagnosed with a learning disability. So the intercept for the latent intercept, how am I going to interpret that now?
Those not having disability.
Yeah, exactly. It's going to be the predicted score at age 6 for those kids who don't have a learning disability, right? And then I'm going to get the effect of LD on the intercept, right? And that's going to be the differential between those without and those with learning disabilities in terms of where they start. And the same thing is going to be true over here on the slope side. Here, the slope is now going to be the predicted growth slope for students without disabilities. And the effective LD fake on slope, right, this path is going to tell me about the differential between those with LD and those without in terms of their growth slopes. Okay, so how am I going to do that? Okay, so here we go. I've got, now I say I'm going to use that LD fake variable. In my model, I still have the intercept in the slope. Now I've got the prediction of, I've got the intercept is regressed on LD fake, and I've got the slope is regressed on LD fake. So this is the part of the model.
Regarding the output, shouldn't we STDY instead of STDY?
Yeah, it should be STDY. Sorry about that. Okay, STDY. It's not actually going to matter here because we're looking at the unstandardized estimates. So we don't really care about the standardized estimates, except for that correlation, which again, but yeah, we'll put STDY there. So STDY, residual, I don't remember why I put Tech 4 in there. We're not going to worry about that. And run. Sure, save changes. Okay, so here we go. Let's get to our, not STDY, sorry, we want our unstandardized estimates. Okay. So there we go. So now we've got if you look at this, the intercept on LD fake is 0.08, which is actually saying that the students with LD have scores that are 0.08 higher, because it's positive, than the students without LD in terms of the intercept, which is at age 6. But look at the p-value is 0.95. That is not statistically significantly different from 0. So basically, this model is saying students with and without LD start at the same place at age 6 in terms of their reading scores, okay? Now, though, I have slope on LD fake, and I got to look at my intercept for my slope now has changed, right? It was 10 before, but now it's actually 12.93. But that's because this 12.93 is now this is the growth slope for students without LD, okay, is 12.93. The differential between students without and students with LD is that slope on LD fake, which is negative 9.29. Right? That's the differential. And so that means 12.93 minus 9.29 is what do we got here? 3, right? So this differential is statistically significant, meaning there is a difference in terms of the rate of growth between those with and without disabilities. Those with disabilities are growing significantly more slowly than those without. And then what would be the predicted bi-yearly growth rate for students with disabilities? It's 12.93 minus 9.29, which gives me 3.64. So students without disabilities are predicted to grow at a rate of about 6.5 points a year, right? I'm dividing that by 2 in my head. Students with disabilities are predicted to grow about 1.67 points per year, again, dividing it by half in my head. And that differential in their growth rates is statistically significant. And finally, I might want to look at these unstandardized residual variances to say, did it look like I'm explaining much of the variance? I had the variances here. Remember, this was like 25, and this was 27.56 were the residual variances for the intercept and slope factors. And now you can see, look, the residual variance for the intercept factor is virtually identical to the last model, which makes sense because remember that this LD variable did not predict at all the starting values for kids. So I'm not actually explaining between person variance and where kids start with this variable. But remember, the variance for the slope before was 27.56, and now the residual variance for the slope is 7.006. So the variance has gone from about 27 point something to 7 point something. So I could go like 27, I'm just going to round here for running out of time, minus 7 divided by 27, right, is 20 over 27, which is, I don't know, a bunch. Let's see. What is that? Somebody help me out. Over 3/4, I think, right? The vast majority of the variance in growth slopes, right? I could easily compute this, but the vast majority of variance in growth slopes is actually being explained by whether or not the student was diagnosed with a learning disability, which again, remember, is not surprising because I totally cherry-picked the data to make this happen. So please, please, please don't assume that this tells you anything about students with disabilities. But, and in fact, after putting that one variable in, the residual variance for the slope factor is not statistically significantly different from 0, right? So I've explained just a ton of the variance in kids' growth rates with this one totally made up variable. Questions? Does that make sense? All right, we did it, we got through everything. So now you can do your homework. The next week we will pick up with where we left off, talk about nonlinear models. Bye. Let me turn this off. Stop.